Hello viewers, welcome to our online channel. I, Dr. Archana Choubey, Assistant Professor, Department of Chemistry from the Bhopal School of Social Science. In the last lecture, we did start with the important topic of physical chemistry, that is phase equilibrium, and we discussed about phase rule and important terms related to it. In today's lecture, we will be dealing with one component system. So let's begin. Today, we will be discussing on the ice water vapor equilibrium, the salient features of phase diagram, vapor pressure curve, sublimation curve, fusion curve, metastable equilibrium, triple point and areas related to phase diagram. If we take the example of ice water vapor system, it is a one component system. We had discussed that what do we mean by one component system? Like we know, water exists in three states: ice, which is the solid state, vapor, which is the gaseous state, and the liquid water in the liquid state. So, it exists in three states, but chemically if you talk about, to describe the composition of each, we need only the formula H2O. That means the composition of each of these three phases is described by only the component H2O. Therefore, it is an example of one component system which exists in three phases. The salient features of a phase diagram is that in a phase diagram, the number of phases which can exist together in an equilibrium, they depend on the specific temperature and pressure condition which we use to make it and represent the phase diagram graphically by taking pressure on one of the axis and temperature on the other. Like in case of ice water vapor system, there will be three curves, one point and three areas which we will be describing to relate the three states of water. This picture that you see, this is an ice water vapor diagram, or it is the phase diagram. First we will discuss the OA curve, which is known as the vapor pressure curve. This vapor pressure curve, if I just darken it, this is the vapor pressure curve, and it divides the whole diagram into two parts where it is showing the equilibrium of the water in the liquid state. This is the part which is showing the liquid state, and this is the part which is showing the vapor phase, or which we may call as the steam. So, the part line OA, it is dividing liquid and vapor, and it is showing the conditions of equilibrium where the two conditions can coexist together. Now, this line or the curve, vapor pressure curve, why it is called vapor pressure curve? Because with change in pressure, we know that the vapor or the gaseous state, on decreasing pressure, cooling process will occur and it gets converted into liquid, while again increasing the temperature, it gets converted into the steam state. So, on applying the phase rule, which is F is equal to C minus P plus 2, putting C is equal to 1 since it is a one component system, and P is equal to 2, because here when you are describing the curve OA, we are talking about the two phases in equilibrium, liquid and gaseous phase. That means the value of P will be 2. Applying the formula and mathematically calculating it, we get the answer 1, which means the degree of freedom for the curve OA is 1. What does this mean? That to describe any point on this curve, you either need to state the temperature or the pressure, and if we fix one of the value, the other value will automatically be fixed. Therefore, such system which has the degree of freedom as 1 is known as a univariant system. The upper end of the curve OA is marked by a point which is known as the critical point. This is the critical point or the critical temperature, the point at which the curve is ending. So, what is the significance of this point? That this point is the critical point and its temperature condition is that the temperature, if we talk about in degrees Celsius, it is plus 374 degrees Celsius at atmospheric pressure of 218.5 atmosphere. So, this temperature is known as the critical temperature of water, beyond which if you go, there will be only vapor phase, and liquid and vapor phase ultimately they merge together and it appears as a homogeneous system. Now, moving to the second curve, which is the OB curve, which you move down way. This is the OB curve and it is known as the sublimation curve. Now, as I told you that this phase diagram, it divides and it shows the three phases of water, where this part was showing the vapor phase, the upper part was showing the liquid phase, and the left hand side is showing the solid state of water. So, now the line OB or the curve OB is dividing the solid state and the vapor phase. As we know technically that any solid when heated, if it directly gets converted into the gaseous state without being converted into the liquid state is known as sublimable solid, and this mechanism is known as, or this phenomena is known as sublimation. So, since here we are correlating the transition of a solid and a gaseous phase, therefore, this curve has been given the name sublimation curve. So, this curve represents the equilibrium between ice and the vapor state. Again applying the phase rule, since it also has, it is a one component system and the relationship is between the two phases solid and gaseous. So, applying the phase rule, F is equal to C minus P plus 2, it again gives the value of F is equal to 1, which is a univariant system, as it was in the case of OA or the vapor pressure curve. Again when you look at this curve, it ends at point B and the temperature conditions over here, it is mentioned as minus 273 degree Celsius, and this point is known as absolute 0. What does that mean? That beyond this, if you go the temperature, beyond this there will be only solid state that will exist and the vapor phase will disappear. Like beyond A, we had discussed for the critical temperature that if we go above the temperature beyond point A, then it will be only the vapor phase and the liquid phase will disappear. Now, coming to the third curve, which is the curve OC. This curve we can see it bends towards the axis of pressure, the two axes that we have taken in the phase diagram. The x axis is showing the temperature and the y axis is showing the pressure condition. So, this curve is known as the fusion curve, because here we are talking about an equilibrium between the solid state and the liquid state. So, here it is talking about the process of fusion, or it can also be termed as melting point curve, because a solid getting converted into a liquid is known as, the process is known as melting. So, the name of these curves have been given based on the process which is occurring between the change of the two phases. Again applying the phase rule, it again gives the answer F is equal to 1. So, we may generally say that all these curves are univariant with the value of degree of freedom as 1. Now, this curve, if we go into detail, the curve is slightly inclined towards the pressure axis, which indicates what? That the melting point of ice decreases with increase in pressure point. And why does it happen so? Because when ice changes into water, this is because the density increases, and when density is increasing, the volume of ice will decrease, because the formula of density is inversely related to volume. That is why the curve is showing this negative slope towards the pressure axis. Now, moving ahead, there is one more line that we see, that is the line OA dash, which is just above the sublimation curve, and this is known as the metastable curve or the point of metastable equilibrium. And this point is what does it show? That it is sometimes possible to cool the water. We know that on cooling automatically water will get converted into ice, but at specific conditions, if we cool the water and instead of getting converted into ice, it remains in the liquid state, but its temperature goes beyond the absolute 0, then such water is known as supercooled water, and it is a highly unstable condition which is very difficult to maintain. So, this curve is known as the metastable curve, where on supercooling the liquid, it instead of getting converted into the solid state, it continues to be in the liquid state. Now, after discussing the 3 curves, we come to the point O. Like when we were talking about all the curves OA, OB and OC, each is starting from a common point O, and this point is a very special point which is known as the triple point. If we calculate the degree of freedom for this point by applying the phase rule, F is equal to C minus P plus 2, taking C as 1 since it is a one component system, but P over here becomes 3 because it is the point where all the 3 lines are merging together, and this is the point where ice, water and vapor, that is solid, liquid and gaseous state, all can coexist, and they will coexist only when the temperature condition will be 0.0098 degree Celsius and the pressure will be 4.5 mm of mercury. So, this specific temperature pressure condition, if it is maintained, then only it is possible to see all the 3 states of water coexisting together. So, that means if we want this the 3 conditions to exist together, we do not have any freedom to change either the temperature or the pressure condition. Therefore, it tells that the degree of freedom for such condition will be 0, or it is known as invariant point. That means there is no degree of freedom and each temperature pressure condition is fixed. It is also known as a triple point. The triple point means that the 3 states exist together, and invariant point means that there is no degree of freedom. So, we must always remember what is the temperature at this point. It is 0.0098 in degree centigrade, or if we are talking about in kelvins, it is 273.16 Kelvin with pressure of 4.58 mercuric pressure. Now, come after discussing the 3 curves and the triple point, we come to the third part, which is the area. In this diagram, if we look, there are 3 areas, which is AOB showing the gaseous state, AOC showing the vapor state and BOC showing the solid state. So, AOC is the liquid state over here, BOC is the solid state and AOB is the vapor state. And each of these areas, when we apply the phase rule, we find out that the areas will be bivariant. That means the degree of freedom for area is 2. So, the first area is, see, this is what I was talking about. The degree of freedom is 2 and it is known as a bivariant system. So, if we talk about the area of AOB, this area, it is representing the existence of only vapor. If you go in any of the point over here with the temperature and the pressure condition, we will come in the area. Therefore, these areas, they specifically tell about the existence of only one of the pure states. Now, if I summarize all the discussion and take this diagram, we can see that the ice water vapor system divides existence of gas, liquid and solid individually in the 3 marked areas, and these lines are showing us the interconversion of either gas to liquid by condensation or liquid to gas by vaporization. Similarly, gas to solid by deposition and solid to gas by sublimation, and thirdly we can say the interconversion of solid to liquid by melting and liquid to solid by freezing mechanism. So, now I hope that by the end of this lecture you must have understood that why in a phase diagram of one component system, how by different pressure and temperature conditions graphically we can represent the interconversion of the three states into each other, and how these phenomena occur by changing the temperature and pressure conditions to establish this phase equilibrium. Okay students, in the next lecture we will be dealing with another example of one component system. Thank you.